So in this video we want to introduce singular matrices. And the idea here is that over the next few homework assignments or lessons, matrices whose determinants are zero are going to be very important to us in the study of matrices. And so we want to give matrices whose determinants are zero a name. So we're going to name them singular matrices. So we're going to say, hey, if we have a square n by n matrix, we say it's singular if its determinant is zero. And then we're going to say it's non-singular, or the opposite of singular, if the determinant isn't zero. So very simple. Singular matrix means the determinant of that matrix is zero. And then that leads directly into a theorem. And the theorem, the theorem does is identifies when or situations for which we are sure that we are working with a singular matrix. So the first case is if any row or column contains all zeros, you'll have a singular matrix. And this would be really easy to prove because all you would do is calculate the determinant using the row or the column expansion where the row or column had the zero. So you'd get 0 times a cofactor matrix plus 0 times a cofactor matrix, and you'd wind up with the sum of a bunch of zeros. So this one would be simple to prove. You would just say, hey, expand in terms of the row or column with the zeros. Case 2 says if any two rows or columns are equal, you'll have a singular matrix. And case 3 says if any two rows or columns are proportional to each other, you'll have a singular matrix. And remember, if you say that one thing is proportional to another, if you say A is proportional to B, all you're saying is that B is a scalar multiple of A. In other words, there's some real number K that exists so that A is equal to K times B. So when we say that two rows or columns are proportional to each other, we're just saying that one row vector or one column vector is a scalar multiple of the other row or column vector. And really this case 2 is just a special case of case 3 where the constant of proportionality is 1. Hey, if two rows or columns are equal, then 1 times the row vector equals the other row vector, or 1 times the column vector equals the other column vector. So 2 is a special case of 3. And you're going to be asked to prove number 3 in the homework. And so what we want to talk about is how you might prove that. And the hint that I'm going to give you is that you should be able to use property 3 of the properties of determinants to come up with a very simple proof for why one column or row being proportional to another will generate a singular matrix. So the key, my hint to you before you do the next homework, is to use property 3 of the properties of determinants. And if you do that, the proof should go pretty easily for you. So on this slide I have 3 matrices, each of which is singular. This matrix A is singular. I should have given these different names. That's a sad thing to do, give them all the same name. So matrix A is singular because column 3 contains all zeros, and clearly if we expanded the determinant calculation with respect to column 3, we would get 0 times a cofactor matrix plus 0 times a cofactor matrix plus 0 times a cofactor matrix would just be 0. This matrix is singular because columns 1 and columns 2 are equal to each other. So in fact, if we took the opposite of column 1, if we did the opposite of column 1 plus column 2 and replaced column 2 with the result, we would get all zeros here. And then if we expanded the determinant with respect to that column, we would find that the determinant of B was equal to 0. So again, using the previous slide of this theorem, this is corresponding to case 2 where we have columns that are equal to each other. And in this matrix C is singular because row 3 is proportional to row 1. Row 1 or row 3 is proportional to row 3 row 1 is proportional to row 3, and we could just as easily say row 3 is proportional to row 1 because row 1 equals, 3 times row 1 equals row 3, or a third of, we could also say a third of row 3 equals row 1. So depending on which way you wanted to look at it, the idea here, row 3 being proportional to row 1, why this would generate a singular matrix is we could easily do 3 times row 1 plus row 3, and then replace row 3 with the result, which would give us zeros here. And because we're using property 3 of determinants, we know that the determinant of C would equal the determinant of the matrix that resulted by applying this elementary row operation. So that kind of wraps up that conversation. Nothing too difficult here. Singular matrix means the determinant of that matrix is 0. And you're always looking, when you're scanning through a matrix, you're looking to see, are there rows or columns that are identical or proportional to each other? And that tells you that you're working with a singular matrix.